Very pleased to have Jiaoyang Huang, who braved the weather and drove here from Philadelphia to tell us about Ramanujan property and edge universality of random regular motion. Exciting result. We're looking forward to an exciting lecture.
Thank you for the invitation, and thank everyone for coming in such a cold day. So I will explain to you our results on Ramanujan property and edge universality of random regular graphs. So this is joint work with Theo. He's at Stanford at HTL, he's at Harvard. So this talk, I will have those three parts. I'll start a very quick background on random graphs and random matrices. And the second part is about our main results on eigenvalue rigidity at edge universality. And last part will be some proof ideas. So if you have any question during the talk, feel free to interrupt me. So the model, we study a random irregular graph model, which is just a uniform probability measure on the set of simple irregular graphs with n vertices. So here simple, we just mean we do not allow multiple edges or self-loops. So here is an example of a three regular graph. I steal it from the article by Peter, what's an expander? The expanders are those very sparse and highly collected graphs. And the amazing thing about the random irregular graph model is they provide rich families of expanders. So in our setting, we just look at a random irregular graph and encode it by the adjacency matrix A. So it's a 0, 1 matrix. The row sums and column sums are both D. So it has a trivial eigenvector 1, 1, 1, 1, associated with eigenvalue D. And for our purpose, we will further normalize the adjacency matrix by square root D minus 1. Then the largest eigenvalue now becomes D over square root D minus 1. And you will see in this normalization, all the other eigenvalues are roughly on the interval from minus 2 to 2. So here is a simulation for random four regular graph. So if you plot the empirical eigenvalue distribution of random irregular graph under our scaling, it will converge to this Kesten-McKay distribution. It's a distribution dependent on the degree D. So it has those two parts. The first part depends on D. And this second part, it does not depend on D. It's a perfect semicircle supported from minus 2 to 2. So as you can see, for this random four regular graph, it has an outlier corresponding to the degree. All the other eigenvalues are on the interval from minus 2 to 2. It matches pretty well with the red curve, which is a Kesten-McKay distribution for D equals 4. And even in a very small bin, the number of eigenvalues is well predicted by this red curve given by the Kesten-McKay distribution. So this Kesten-McKay distribution first discovered by Kesten when he studied the spectral measure of infinite irregular tree, and by McKenzie for irregular graphs. And for us, we care about the eigenvalue gaps, the spectral gap, the gaps between largest and second largest eigenvalue. So they measure the expanding property of the graph. So looking for good expanders, it's the same as looking for random graphs with a large spectral gap. So the actual question is, what is the largest possible spectral gap? And this question was answered a long time ago by Allen and Bopana, so in 1986. So they show for any collected irregular graph, there exists some universal constant CD. Second largest eigenvalue is lower bounded by 2, subtract the constant over the diameter of the graph. So if you have a sequence of irregular graph, the size n goes to infinite, then the diameter is at least log n. So symptotically, lim-inf of the second largest eigenvalue is at least 2. The largest possible spectral gap, or symptotically, is just lambda 1, which is a degree, subtract 2. And because of this, in the famous paper by Lubatsky, Philip, and Peter, they coined the term Ramanujan graph. So a irregular graph on n vertices is called a Ramanujan graph. If under our scaling, it's all the non-trivial eigenvalues are bounded by 2. So in the non-bipartite case, you ignore the largest eigenvalue. For the bipartite case, you ignore the largest and smallest eigenvalue. So symptotically, those Ramanujan graphs, they are best spectral expanders. They have largest possible spectral gaps. And in the same paper, Lubatsky, Philip, and Peter, they give explicit construction of Ramanujan graphs for degree D, which is prime plus 1. And the construction was also given independently by Margulis. And to show those graphs are Ramanujan graphs, they use some version of Ramanujan conjecture. That's why they are called Ramanujan graphs. And since then, Ramanujan graphs has found a lot of applications. I will not elaborate. And one major problem is, does there exist infinite family of Ramanujan graphs for any degree D? And this question was only answered 10 years ago by Marcus, Spielmann, and Shrivastava. They prove there do exist infinite family of bipartite deregular Ramanujan graphs for any degree D. And their first proof is an existence proof. And later, a polynomial algorithm was proposed by Michael Cohen. So it still remains an open problem. Does there exist long bipartite Ramanujan graphs for any degree D? If you have a long bipartite Ramanujan graph, and look at the bipartite double cover of it, you will get a bipartite Ramanujan graph. But from the simulation, there should be a lot of Ramanujan graphs. So it's observed if you sample a random deregular graph, look at the second largest eigenvalue or smallest eigenvalue, that will modeled by the Tracy-Widom beta equals 1 distribution. They come from the Gaussian Orthogonal Ensemble, GOE. So here is some quick introduction of random matrix theory and some statistics we will use. So for the Gaussian Orthogonal Ensemble, it's just an n by n large real symmetric matrix. So all those entries in this upper half triangle, they are independent Gaussian random variables. They have mean 0, and the variance, the diagonal has variance 2 over n, and off diagonal, they have variance 1 over n. The variances are chosen in this way. The whole matrix is orthogonal invariant. If you conjugate it by orthogonal matrix, the law does not change. And similarly, you can look at the complex version of it, the complex Gaussian matrix, that's called the Gaussian unitary ensemble. So if you plot the eigenvalues of GOE, you get a perfect semicircle from -2 to 2. It was proven by Tracy and Widom. If you take out the largest eigenvalue, it's close to 2, subtract 2, and rescale it by n to the 2/3, it converges to a distribution, we call it Tracy-Widom beta equals 1 distribution. And if you do the same thing for the complex Gaussian matrix, you will get a Tracy-Widom beta equals 2 distribution. It's just convention in random matrix theory, beta equals 1 for the real symmetric case, beta equals 2 for the complex Hermitian case. And here is the plot for the Tracy-Widom beta equals 1 distribution. If you just look at the shape, it's really look like just a Gaussian distribution. The main difference is because the Tracy-Widom distribution is defined in this way. So it's not centered. The mode is not at 0. Most of its mass is on the negative side. In fact, 83% of the mass is on the negative side. So from this, you will have 83% of those Gaussian orthogonal ensemble, lambda 1 is less or equal than 2. And later, this phenomenon, this convergence to the Tracy-Widom distribution was also proven to be universal. So essentially, you take any large real symmetric matrix, fill in any distribution you want, as long as it's real symmetric. Entries are independent, has mean 0, variance 1 over n, and those entries has a bounded force moment. After this scaling, you always get a Tracy-Widom distribution for beta equals 1, real symmetric case, or beta equals 2 for the complex Hermitian case. And so maybe motivated by those edge universality, it was speculated by Peter and Miller, Novakov, Simonyi, both based on extensive numerical simulations. Conjecture for random deregular graph on n vertices. If you take out the second largest eigenvalue, subtract 2, rescale by n to the 2/3, like in the GOE case. And then you need to further normalize it by C1D, and maybe possibly some shift should converge to a Tracy-Widom distribution. Same statement holds for the smallest eigenvalue. So here are some simulations I did. If you just take out the second largest eigenvalue, subtract 2, rescale by n to the 2/3, I just get this by sample a lot of random deregular graph and plot the empirical distribution for lambda 2. It's the blue part. If you do it for GOE, it's red part. They will look different. But if you just center them to have mean 0 at variance 1, then GOE at a spherical graph, they look actually quite close to each other.
What are C1 and C2? I mean,
So yeah, it's actually from the simulation, it's not that easy to figure out what are those constants.
Those are specific.
Yeah, they are constants. So so you can think this is really this part, the blue, and the red one is the Tracy-Widom. It's just there should be some constants, such as the two will match each other. And here is the picture I steal from Miller, Lovikov, and Savarli's simulation. They compute the percentage of random spherical graphs from different models. Here, different curves will correspond to slightly different models for those random spherical graphs. And the vertical axis is the percentage lambda 2 is less or equal than 2. Horizontal axis are the number of vertices go from 0 to 20,000. As you know, you can see this slowly converge, but it's pretty small. And this yellow dashed line, this yellow line is 83% from the Tracy-Widom distribution if this C2D is 0. So they are close, but not for sure. And our main result just tells you, in fact, this shift should be 0, and the percentage should go to 83%. Okay, so next I'll explain the main results. So like for those random Dirichlet graphs, even to show the second largest eigenvalue concentrated around 2, it's not easy. It's actually pretty hard. It was the first conjecture by Allen. Like for random Dirichlet graph, they should be nearly Ramanujan. The second largest eigenvalue should concentrate around 2. This conjecture was first proven by Friedman in 2004, and later a shorter proof discovered by Vodinov. They show for random Dirichlet graph with n vertices with probability close to 1, the second largest eigenvalue concentrate around 2. And this error they can get is log n over log n squared. But if that edge universality is true, this error should be n to the minus 2/3. Later in a joint work with Yao, we managed to show some slightly better bound, like polynomial bound n to the minus c, but this c is really small, like it's 0.01, something like that. And you can think those random Dirichlet graph, it's can also, another model for random Dirichlet graph is to think it as a random uncovering of some base graph. Base graph is 2 vertices at the d edges between them. And in general, you can study random uncovering of any base graph and look at their extreme eigenvalues. There are a lot of researches in this line, like I will not elaborate. And last year, Chen, Garzavaga, Strop, and Roman, they developed a very nice new approach to prove the strong convergence of random matrices. Their approach works for many matrix models, specialized to random Dirichlet graph. It tells some polynomial concentration of second largest eigenvalue bounded by 2 plus 1 over n to the 1 over 6. And our first main result is about those concentration of the eigenvalues for random Dirichlet graphs. So to state it, let's first fix any degree d. And we know the empirical eigenvalue distribution converges to the Kesten-McKay distribution. So we denote the classical eigenvalue distribution of the Kesten-McKay distribution rho d as gamma I. The integration from gamma I to 2 equals I over n. In terms of this picture, those gamma i's are just 1 over n quantiles of the Kesten-McKay distribution. So we prove with high probability close to 1 minus some n to the minus c. The ith eigenvalue concentrates around gamma I. And the concentration, the bound is given by n to the minus 2/3 plus little 1. This can be arbitrarily small. And this eigenvalue I at n minus I plus 1, the smallest of the two to the power minus 1/3. So let me just help you parse a little bit what this expression tells about. So if you look at those extreme eigenvalues, like lambda 2, lambda 3, or the lambda n, then this I is 2 or 3, or I is n. This second factor is of order 1. So it's a constant, you can ignore it. So which means those extreme eigenvalues concentrate on the scale n to the minus 2/3. And now if you look at the eigenvalues inside of the block, I is Cn over 2. Then this second factor is of order n. So this two factor together, you will get n to the minus 1, 1 over n. This is also the best possible one can hope, because from minus 2 to 2, there are n eigenvalues. So typical gaps is 1 over n. So this basically is the fluctuation of those eigenvalues is roughly the order of the gaps. This is the best one can hope. This also explains this picture. If you look at a very small bin, as long as the width of the bin is much bigger than 1 over n, the number of eigenvalues inside this bin is well predicted by the Kesten-McKay distribution. So this is a concentration of eigenvalue. So the next the result is about the edge universality. So we basically confirm this conjecture. We show for random de-Rigueur graph, if you take out lambda 2 minus 2, and rescale it by this factor a, which is a number depends on the degree d, a times n to the 2/3, then it converges to the Tracy-Widom distribution. So in terms of those constants, it's just this C2d, it's 0, and the C1d, it depends on the degree d. So it's some normalization constant depends on degree. And the reason for this C1d is because if you look at those Kesten-McKay distribution, zoom in around the edge, which is at the location 2. So for the Kesten-McKay distribution, if you zoom in around the 2, it has a square root behavior. It behaves like this constant a times the square root of 2 minus x. And if you do the same thing for the semicircle distribution, and it also have the square root behavior at edge 2. For the semicircle distribution, you will get the square root of 2 minus x. So this normalization by this constant a is just to make the curvature the same. And so this is for the fixed d. And if you allow the degree d to grow with the size of the graph is not that sparse. And that was studied before. And yet, in fact, the sparser is usually harder. So when d grow, it's easier. It's closer to those Gaussian matrices, which are pretty dense. So first, in the joint work with Roland and Antti, we can prove this edge universality when d is bigger than n to the 2 over line, much smaller than n to the 1 over 3. And you can prove it when d large, d is bigger than n to the 2/3. And 2 years ago, together with Yao, we can show as long as the d grow arbitrarily small, like n to the epsilon, you will have edge universality. And finally, we can prove when the degree d is a fixed number. Then back to the story of Ramanujan graph. So actually what we prove is slightly stronger than this one. We can prove the second largest eigenvalue and smallest eigenvalue, they are symptotically converge to independent copies of those Tracy-Widom distribution. So we will have, for Tracy-Widom distribution, 83% of the mass is on the negative side. So 83% of the chance lambda 2 is less or equal than 2. And then 83% of the chance lambda n is bigger or equal than minus 2. So they are independent. Then multiply them together, we get 69% of those de-Rigueur graphs. They are Ramanujan graphs. Actually, more than half of those de-Rigueur graphs are Ramanujan graphs. So this is about the results for the eigenvalues. So eigenvectors is also of great interest. So here I will just quickly comment about some results for the eigenvectors. The eigenvectors are interesting because regular graphs, they are simplified, yet very insightful models for those quantum chaos. So one can study a sequence of deterministic regular graphs. As long as this sequence, they are expanders, and under very mild assumptions of injectivity radius. And one can show the eigenvector non-localization first studied by Brooks and Linda Strauss. They prove for essential eigenvectors, they do not localize on a very small set. And later, more refined bounds are proven by Allen, Ganguly, and Shrivastava. And also for the quantum ergodicity for both regular graph case or non-regular graphs case are proven by Nalini, Masson, and Savory. And of course, there is a parallel story for those results for Riemannian manifolds. All of you know more than I do, so I will not comment on that. And if you want to understand random regular graph instead of deterministic sequence, you can prove some more refined properties. So in the joint work with Roland and Yao, we can show another version of those delocalization of eigenvectors in the L infinite sense. If you normalize eigenvector to have a total norm 1, we can essentially show those entries, it's of order 1 over square root n, so completely delocalized, as some version of probabilistic quantum unique ergodicity. And for this random regular graph, you can even ask more refined questions like, what does those eigenvectors look like? Like this picture, if you look at one point of the graph and look at a small radius, then this radius will be just a tree, a truncated tree. And you can ask, what does the eigenvector look like in this neighborhood? And this question was answered by Backhaus and Zigidi. They prove they converge to the so-called Gaussian wave. So Gaussian waves, they are associated with the eigenvalue lambda. It's a Gaussian process on infinite irregular tree. So each vertex, you associate it with a Gaussian random variable, and they are jointly Gaussian. And they satisfy those eigenvector relation. And further, you require the law, this Gaussian process is invariant under any automorphism of the irregular tree. So under those assumptions, Allen proved the existence and uniqueness, essentially those three properties, jointly Gaussian, eigenvector equation, and also invariant under automorphisms. Then those up to any constant, you rescale it, it's still a Gaussian process. So there is one constant, which is a variance at each side. Those three properties uniquely determine the Gaussian wave. And Backhaus and Zigidi, they prove for random irregular graph, if you look at almost eigenvectors, those eigenvectors converge to the Gaussian waves. So it converges in the sense, exactly in this picture I show you, you randomly pick one side and look at a neighborhood, small neighborhood. The small neighborhood will be a tree with high probability. And you restrict the eigenvector to this neighborhood, it converges to the Gaussian wave with some variance between 0 and 1. And in their proof, they study almost eigenvectors. Those almost eigenvectors can be pretty localized, so it's possible those variance will be 0. So the result by Backhaus and Zigidi, you can view it as some graph theoretical result for Berry's random wave conjecture, which suggests the eigenfunctions of a chaotic system behave like a Gaussian random fields. But one slight thing which is not very satisfying about this result is they do not know the variance. So for the eigenvectors, we believe the variance should be 1. It should not be localized. So in ongoing joint work with Yukun and Yao, we can show this variance equals 1, at least for the edge eigenvectors. So if you sample random irregular graph and look at those eigenvectors U2, U3, UK associated with those extreme eigenvalues, they will converge to independent copies of those Gaussian wave with eigenvalue 2 times square root d minus 1, because they are edge eigenvalues. And the same statement holds for the smallest eigenvalues. So those are the results I will discuss. So far, any questions? Now it's maybe a good time for questions. Okay, so next I'll explain to you some main proof ideas.
Just to be clear, you don't know how to do the at the edge you can do it, but not in the interior. You don't know.
Yeah, so all those results are for
so 2/3. You just squeak in at 2/3.
Yeah, Peter's question is usually for those questions, like for example, irregular graph, it's a good model for quantum chaos. It's usually refer for the eigenvalues, eigenvector inside the Bach.
Yeah.
And there is also a version for Bach universality. Look at those eigenvalue gaps inside of the Bach. that should also asymptotically the same as the GOE matrix. So far, we cannot do it. Usually for the bulk, it's harder than the edge because the edge, the scaling is n to the minus 2/3. For the bulk, it's 1 over n, which is much smaller. But for that, that should be true. And there's also very robust simulation and physics, like heuristics. Everything, the universality should be true. Other questions?
So just to clarify, you have near optimal spacing in the bulk.
Yes.
You had it before, you had it at the edge, I think. But you don't have the universality in the bulk.
Yeah.
So how come the bulk spacing is easier, but the bulk universality is harder?
Also, so in like if you think about those estimates in the edge, so we also have complete delocalization of eigenvector as edge. So for all the estimates, we can also go to 1 over n. So in that's but for the edge, we only did n to the minus 2/3. So at least at the scale n to the minus 2/3, we have all the estimates, and we can iterate to get the better estimate. But for the bulk, you want to ask a question on the scale 1 over n. We only have it up to some log factor. We don't have it exactly down to 1 over n.
But maybe you can say a word about moments versus Green's. Okay, you'll explain your methods in a minute. But in random matrix theory, at the Tracy-Widom at the end, I think you mentioned Shoshnikov was able to do it with moments, while in the bulk, nobody can do it with moments. So
it's also the history of random matrices first proves the edge and then the bulk. So
I'm trying to highlight the fact when you can do it with moments or without moments. I guess after your talk, it'll be clear.
yeah,
what you're
I'll
doing.
come to the moments. Yeah, so for the proof, we use a lot of techniques from random matrix theory. So here I will mainly highlight two new ideas, which is used to prove the edge universality. One is a microscopic version of loop equation. Another is a generalized switching procedure. So the loop equations, they are first developed in the physics community from the 2D quantum gravity studied by many people in the next door here. So here is a well-known result related to the moments. If it's about counting surfaces. So if you look at an n by n Gaussian unitary ensemble, you can look at its moment, trace of the case moment. It essentially gives you the case moment of those eigenvalues. So this trace of the case moment it has those 1 over n expansion. And this 1 over n expansion, the coefficients, SGK, they count the number of distinct ways to glue the edges of a K-gun in pairs, which give you a surface of genus G. So of course, here K need to be an even number, otherwise everything will be just 0. And there are also similar formulas if you look at the product of traces of powers. Those formulas are first discovered in physics community and also then in the math community. And if you just write down the formula trace of h to the k, because they are Gaussian, you can compute it. But I will promise you, many of you here study those problems, it's very hard. It's actually not easy at all, although everything is just Gaussian. And loop equations is a techniques developed in physics community to compute those moments, get 1 over n expansion. And there are many ways to formulate loop equations. One way is through this Stieltjes transform. So the Stieltjes transform of empirical eigenvalue distribution is just sum of those 1 over eigenvalue lambda I minus z. It's 1 over n. You can also get it from the Green's function if you look at the trace of matrix H minus Z inverse. And formally, if you do a Taylor expansion of Z when Z is large, you will get those trace of moments. So you can think Stieltjes transform is a way to encode those moments. And if you have the Stieltjes transform 1 over n expansion, you will also have those trace of moments 1 over n expansion. And so here is the loop equations for those Gaussian orthogonal ensemble or Gaussian universe.
So just a second, the previous slide. Oh, just You just slow. You could it's that.
Yeah, other questions, sorry. So here are the loop equations for Gaussian orthogonal ensemble, Gaussian unitary ensemble. So for Gaussian orthogonal ensemble, Gaussian unitary ensemble, you can actually write down the joint eigenvalue distribution. It's given by this formula called the Gaussian beta ensemble. When beta is 1, it's GOE. When beta is 2, it's GUE. So this Gaussian beta ensemble is well defined for any beta bigger than 0. They interpolate the GOE and GUE. And there are a lot of amazing properties for the Gaussian beta ensemble. For example, those normalization constant you can compute it by the Silberg integral. And there is a nice tridiagonal models which has the eigenvalues given by those Gaussian beta ensemble discovered by Edelman and Dumitru. And if you look at the Stieltjes transform of those Gaussian beta ensemble, they satisfy the loop equation just described with some recursive structure satisfied by those Stieltjes transform. Here is the first loop equation. It has these two parts. First part is some quadratic one in terms of Sn squared plus Zsn plus 1. And second term is some 1 over n correction, depending on the derivative of Sn. So this is just some, if you compute the expectation, it's exactly 0. And you can also have a higher order loop equations, which is more complicated, but the core is still this blue part. And you multiply several other copies of Sn, p minus 1 copies of Sn at different locations, Z1, Z2 up to Zp minus 1. And then you have a further 1 over n squared correction. And there is this complicated expression. But essentially, it just boils down to p minus 1 copies of this Stieltjes transform multiplied together. So those are loop equations for the Stieltjes transform. You can also interpret it as some correlation function. So you encode all the informations of the eigenvalues if you zoom in around the spectrum. So if you think it this way, they are exactly the Dyson-Schwinger equations for those matrix ensembles. In general, Dyson-Schwinger equations refer to those recursive relations among correlation functions in quantum field theory. And for those loop equations, usually they are obtained by, like for the GOE or GUE, you can use matrix models to do integration by part, Gaussian integration by part. Or for this Gaussian beta ensemble, you can also directly do an integration by part to get those equations. They're not that hard to get the equations. And the hard part is to analyze those equations. Although they are complicated, but you can analyze them and get 1 over n expansions of those Stieltjes transform. And more generally, you can also look at those so-called beta ensemble. Instead of here just lambda I squared, you can put any potential V here. And so these loop equations, you can also write down for those beta ensembles. They play a very important role, improve the eigenvalue rigidity or universality for those beta ensembles. But in general, if you write down the loop equations for those models, they are model dependent. Like for the beta ensembles, if you write down the loop equations, they will depend on the potential V. So they will be model dependent. However, the key observation we will use is if you zoom in around the spectral edge too, also zoom in, just blow up those loop equations. In fact, you will get something universal. And that's we call the microscopic version of loop equations. So if you look at the eigenvalues of the Gaussian orthogonal ensemble, I discussed if you scale the lambda 1 by n to the 2/3, it converges to the Tracy-Widom distribution. You can also do the same scaling, subtract 2, and multiply n to the 2/3 for all those extreme eigenvalues all together. Then you will get this area 1 point process. It's a point process. You will have a capital lambda 1, lambda 2, lambda 3. It's a random point process. It's an infinite point process. And the first for beta is 1 or 2. It was proven first by Tracy-Widom. For general beta, it was proven by Ramirez, Ryder, and Virac. And for this limiting picture, the every one-point process, we can also define the Stieltjes transform. Just define this YW as sum of 1 over those particle locations lambda I minus W. If you naively just compute this quantity, it will blow up. So you need to do some further normalization. So this is a well-defined quantity. And this is really just some random meromorphic functions with a pose given by those particle locations lambda 1, lambda 2, lambda 3. So as you can imagine, they really encode all the informations of this every one-point process. And because of the square root behavior, like the density of those particles has a square root behavior, which also induces this YW. It has a square root W behavior when W goes to infinite. So if you blow up those loop equations close to the spectral edge too, then you will get some equations, although they are still quite complicated, but they are universal. You always get this set of equations. Like the first one is some quadratic guy, depend on this YW subtract square root W, plus some correction which depends on the derivative of YW. And the higher order loop equations are this one still the red part, times p minus 1 copies of y at different locations. And this last term is just involve p minus 1 copies of y. It's always some recursive relations depend on here is you can think it's a p plus 1 point correlation and a p point correlation and p minus 1 point correlation. It's just those equations which tells you some relations of those correlations. So from this you can see if I have some point process like the eigenvalues of Gaussian beta ensemble, if we believe they converge to the every one-point process, then it's necessary some scaling limit of the Stieltjes transform. After taking the scaling limit, they will converge. They will satisfy this set of equations. It really should be a necessary condition. So what we prove the edge universality is essentially check those microscopic version of loop equations for random de-Rigueur graph. So back to random de-Rigueur graph, we normalize the adjacency matrix by divided by square root d minus 1. And the Green's function is h minus the inverse. H is in the complex plane. And the Stieltjes transform is 1 over n times the trace of the Green's function with summation of those 1 over lambda I minus z. So we know the empirical eigenvalue distribution converges to the Kesten-McKay distribution. So the Stieltjes transform of the empirical eigenvalue distribution, it should also converge to the Stieltjes transform of the Kesten-McKay distribution. Explicitly, you can compute it. It's given by this guy. And if you zoom in around the edge location 2, it has the square root behavior given by this A times the square root 2 minus z minus 2. Essentially, it's, if you look at the imagined part of the Stieltjes transform, it recovers the density. So the main result we prove is for random de-Rigueur graph. If you look at the Stieltjes transform, subtract the deterministic guy computed from the Kesten-McKay distribution, this delta z. It satisfies this set of equations. It mimics those loop equations I just showed you. So also first part, the blue part is something quadratic in terms of delta. And you have this 1 over n correction of the derivative of mn. And you have a product of those delta z at p minus 1 different locations. And also this correction term. And you need to
exponent on the n there. Less than what's into what?
Oh, so here is basically we need to check this relation. And the error, it has to be pretty small, much smaller than n to the minus p plus 1 over 3. So this depends on p. You can look at those p copies multiplied. So it's just anything, you can think this is something further, you subtract epsilon. So the reason you want the error to be small is now if we look at blow up this Stieltjes transform, look at zoom in around the edge location 2. And because the scale, the eigenvalue gaps is on the scale n to the minus 2/3. So we just zoom in around the edge location 2 on the scale of essentially here you can think is 1 over n to the 2/3. as you multiply by some n to the 1/3, this quantity, the Stieltjes transform, converges to this Stieltjes transform of every one-point process. And you need to make sure after this scaling, you multiply some n to the 1/3, this error term still goes to 0. So at the end, you will get the limiting version of those loop equations. So once you have this, but here I mentioned to you, this is a necessary condition for the universality. But at this moment, we do not know. It's unclear to us whether those loop equations uniquely characterize every point process. We don't know if it's sufficient. So there is some extra work I need to do. So essentially, to derive those array statistics, we need to analyze this more complicated model, the adjacency matrix plus some squares t, which is a small number, times a GOE. So those Gaussian divisible model. And we actually check the Stieltjes transform for this whole family of models for any t. They all satisfy these loop equations. And combined with some earlier work, we can conclude.
So wait a minute. That's just to compute the answer.
Yeah.
I mean, you have the limit exists before then.
Yes, so we have the limit
You
exists.
just want to make sure that it's Tracy-Widom or the point process. So that then you add this random GOE to your discrete model just to determine the limit.
Yeah, because now essentially what we are missing is a solution unique or not? So essentially this part plays that role. We're trying hard to make this a characterization of those every point process. Hopefully we can see
What's
something.
the parameter T then?
That's the deformation that they make.
Yeah, that's essentially the definition, the how big the GOE part you add to
So do
it.
you believe the solution is unique?
Like the physical solution is unique. Because you must know for those word identity or dice loop equation, the solution should not be unique. But basically meaningful one, if we add some extra, it comes from point process, maybe it's unique.
I see, but it's not technically unique, you think?
Yeah, like I don't think it's technically unique. If you don't know it, they come from point process. Okay, so next I will show you, this is one main idea, those microscopic version of loop equation. Next, I will show you another idea, how do we prove those loop equations using a generalized version of simple switching, using the randomness of those irregular graphs. So I will show you how to prove like the first loop equation, this delta, which is the Stieltjes transform, satisfies this quadratic equation plus some correction, and the error is small, much smaller than n to the minus 2/3. So I will start with this Gaussian orthogonal ensemble. So for the Gaussian orthogonal ensemble, the empirical eigenvalue distribution converges to the semicircle distribution. The semicircle distribution, if you compute the Stieltjes transform, M semicircle, it actually satisfies this very nice algebraic equation m squared plus zn plus 1 equals 0. And it's a fact for a lot of those distributions which show up in random matrix theory, they all satisfy some algebraic equation. And so it's known like a long time ago from random matrix theory, if we want to show the Stieltjes transform of the GOE Mn is close to M semicircle, so if we have the two are close, we will get eigenvalue rigidity concentration of eigenvalue. We do not want to directly compute Mn is close to M semicircle. Instead, we will try to show Mn satisfy the same equation as the M semicircle. Just the same equation, replace it by the Stieltjes transform of GOE, Mn squared plus Zmn plus 1. I compute the expectation. I show actually this is small. The bound is of size, you can roughly think it's 1 over n. You can control it by the Mn by itself. And if you further show high moment of this quantity is also small, then by the Markov's inequality, you can show you get Mn satisfies the same equation, and Mn is close to the M semicircle. And how to get the loop equation? Essentially, For this error, for the Gaussian orthogonal ensemble, you can explicitly identify it. It's exactly given by this 1/n correction term. And now once you take the difference of this first equation and second equation, rewrite it as the equation of Mn minus M semicircle, you get exactly this equation. So here, this factor, if z is close to 2, this is essentially 2 times the square root z minus 2, this first term. So you can roughly think in this setting, at least in our setting, those loop equations is essentially some self-consistent equation plus a correction term. So next I will first give you a heuristic how to guess those self-consistent equation for random de-Rieger graph. And how do we use those generalized switching to identify the correction terms? So for random de-Rieger graph, a key property I have mentioned several times is if you take some log n radius, here c is small. Most of those log n radius, they are just a truncated de-Rieger tree. They do not contain any cycle. Even if they contain a cycle, you can condition on the case they do not contain too many cycles. So you can assume they at most contain 1 cycles. Now back to the Green's function. So one way to interpret those Green's function is just interpret it as the sum of those weighted paths from vertex I to vertex j. You just do this Taylor expansion. Look at, for example, h to the power 3, look at ij's entry. Essentially the number of paths from I to j of the length 3. And you just put those extra weight depend on this 1/z. You can think the Green's function ij's entry is just some weighted sum of paths from vertex I to j. Now we want to compute the Stieltjes transform Mn, which is given by the trace of the Green's function divided by n. Essentially, those are the Green's function on the diagonal entries. So we need to compute the Green's function like GOO. So if you interpret it as the sum over the paths, so you start from vertex O, essentially those paths you leave, you can fix some large neighborhood, maybe log n, radius is log n. It may leave this neighborhood and come back at some other location, or you leave at the vertex J and come back at the same location. So if you just believe most of the neighborhoods, they do not contain a cycle, then the contribution from the first picture should be negligible. Otherwise, they will form a cycle. So most contribution should just come from the picture. You leave the vertex J and come back at the same location, same vertex J. And then in this way, for the part of those paths outside this neighborhood, you can just first sum them up. They're essentially those paths starting from J and come back to J, which does not enter this neighborhood T, which is again given by the Green's function at the vertex J with the neighborhood T removed. And then you can further approximate it by the Green's function at J with the vertex I removed. Essentially, you can think the path from J back to itself, which does not meet the vertex I, then very likely it does not enter the neighborhood T at all. So the two should be close to each other. Again, use a large neighborhood is like a tree. So then the Green's function at the root vertex O can be approximated by this picture, the Green's function of this truncated tree. And you attach some boundary weight given by like the GJGI on all those boundaries. So the quantity we use to write down the self-consistent equation is this quantity Q, which is essentially the average of those quantities, Green's function at vertex J with the vertex I removed. Sum over all the edges ij, they are n times d directed edges. So we normalize it by 1/d. And for this quantity Q, you can just look at each of those Green's function GJGI, repeat what I just showed you in last slides, compute the Green's function of this guy with vertex I removed. It's the same as attach some boundary weight Q on those boundary vertices. Then the Green's function GJGI can be approximated by the Green's function of this picture, which is essentially the Green's function at the root vertex of this truncated d-1 array tree. It's a truncated tree. The root vertex has degree d-1, and all the other vertex has degree d. we denote this function as FQ, which is a Green's function for this picture. And Q is just a boundary weights attached at those boundary vertices. Although this FQ is still quite complicated, but it's explicit. It's just a tree computation. You can compute it. And the self-consistent equation we get is Q should be approximated by this FQ. This is the self-consistent equation we will use. And this equation, you can just really sit down and compute it and solve it. It's the solution of Q equals FQ is exactly given by M semicircle, the Stieltjes transform of the semicircle distribution. And if you just plot in this M semicircle for the computation for the GOO, then you will get the Stieltjes transform of the Kesten-McKay distribution, which is exactly what we want. So this somehow indicates this should be the correct self-consistent equation. And so this is a heuristic for the self-consistent equation. But as I mentioned, this is just a heuristic. Even the first step does not make any sense. If you send the approach to the spectrum, this Taylor expansion does not make any sense. So to verify, really derive this self-consistent equation and get the correction term, it comes to the second main idea is just some generalized version of this simple switching. We can use it to get the self-consistent equation and identify the correction term. So for the simple switching, it's introduced by McKenzie when he counted some subgraph in random Dirichlet graph. It's this very simple procedure. You just look at two edges, just take any two edges, remove them, and replace them by this red ones, V1, V4, and V2, V3. So this simple procedure, it preserves the degree. It also preserves the underlying measure. So if you start from a random Dirichlet graph, you will get a random Dirichlet graph. This also provides a Markov process. You can sample those random Dirichlet graph. This was first used to study those random Dirichlet graph eigenvalues in the work by Roland, Antti, and Yao. So what we will do, we will look at the Green's function at any vertex. So we will just look at a generalized version of this local resampling. Essentially, if we want to know the Green's function at some vertex here O, we just take a large neighborhood. See the radius is log n. And for each of those boundary edges, we randomize them, just do a random switching. Just for each of those boundary edge, we pick another edge in the remaining of the graph. And for this one, we pick another edge here and do a simple switching for each of those pairs. Essentially, you can think this picture, we randomize the boundary edges. And in this way, if the original graph is G, the new graph is G tilde, because simple switching preserves the measure. So this generalized version, we call it the local resampling. It also preserves the measure. G and G tilde have the same law. And another important property is like if you do those simple switching twice, you will get back to the original graph. So it's in fact an involution. So G and G tilde, they not just have the same law, they in fact form an exchangeable pair. G tilde have the same law as G tilde G. So once you have those exchangeable pair, then you can use it to do some discrete integration by parts. So the way we get those loop equations, get to the self-consistent equation, is to use this local resampling to do the discrete integration by part, like the Gaussian integration by part. So here is one slide, quick slide to explain some more details. So essentially, what we did from this local resampling is you take out this neighborhood and replant it back into those randomly picked locations. Because for most of those vertices, they will have a large tree neighborhood. So if you plant it back in randomly picked locations, the boundary effect is really the same as attach some boundary weight Q to those vertices. And with high probability, those vertices will be far from each other. So the boundary weight, they will not interact with each other. So this is how we get to the self-consistent equation Q minus FQ. And mathematically, if you want to derive it, you can use the Schur complement formula, which is some formula allow you to compute the inverse of Green's function. So I will not bother you with this formula. So essentially, the idea is just use this local resampling to identify this self-consistent equation and get the correction term, which gives the loop equation. So if you look at this equation, you may feel it's actually not that complicated. But the key challenge here is to show this error is small, like smaller than n to the minus 2/3. Then after scaling, it will vanish. So to show this error is small, turns out we need to do this local resampling for many times. Like, in fact, we will do it for arbitrary many times. Every time we do a local resampling, we will get some improvement for the error by 1/n to the epsilon. So we need to repeat it for many times. Essentially, the error will be smaller than n to the minus 2/3. And during the expansion, we will get many terms. We need to track those terms. And they occupy the main part of our papers. It's really more than 50 pages of painful computations. So similarly, you can derive the equations for Mn, and then take the difference. You will get the first loop equation.
This value of 2/3 sort of, what's the difference here, this type of calculation, if it was 2/3 or 3/4 or something? I mean, why 2/3 is sort of important for you? Like 2/3 is better than.
Yeah. So why 2/3 is important is here eventually we will look at some limits of those future.
No, I know why you want it, but why can you do 2/3 and you can't do other things?
Oh, so why? So essentially, it comes from this this correction term. This correction term is if you compute it at edge, this term is of order n to the minus 2/3. So if you correct it, the thing you should expect is something slightly smaller than n to the minus 2/3. And this will be enough. I don't know if you can identify further correction. Probably you can. Like for those loop equations, you can have full 1/n expansion. So this you can think is the first correction in the 1/n expansion. You can also look at the next term and the third term. But for the universality, we only need the first correction. Yeah, other question?
The exponent of 2/3 or something like that is very common at the edge with Tracy-Widom, like in the longest increasing subsequence. It's also
Right.
n to 1/3 or something.
Yeah, it's amazing.
It is a surprising thing. It's not a square root.
No, that's fine, but I was sort of wondering why the technology is limited to the edge and you can't apply it to the bulk. And I guess the answer is that this term, whatever it is, this complicated term with the derivative with respect to z is of size n to the minus 2/3.
Yeah, that's a good point. Is we expect there probably should also be you can also zoom in those loop equations inside the bulk. There is also a microscopic version in the bulk. So the question then becomes: you want to show the similar expressions in the bulk for this one, and in the edge. For the edge, the one good thing is. We need to prove this when z is close to the edge on the order of 1/n to the 2/3. And we start from some estimates we know which is true when z is 2 plus 1/n to the 2/3. Even for 2 plus some log n power over n, we have some estimates. So we just start from those estimates bootstrap. But if you want to study the bulk, you should first have some prior estimate when z is some number plus 1/n. So at this time, we do not have that input. But if you have those inputs, probably you can just try to run this recipe to prove the bulk. But it technically will be harder.
Why do you need more than one loop equation? This is the first loop equation. You had a whole bunch of them with extra points.
Yes. So for this loop equation, so you can think the one loop equation is some relation between 1 point correlation and a 2 point correlation, because when you expand it, this is a quadratic term. But if you just have those loop equations, you don't know how to extract the information from it. Like you want to ask what is the distribution at the edge, or what is the percentage which lambda 2 is smaller than 2. But if we have the full loop equation, it tells you all the correlation function, we can extract the information.
You need to understand the Stieltjes transform as a random process in Z.
Yeah, you need the whole process to get the information of the whole point process. So I'm running out of time. So here is Gaussian wave also comes from those local resampling. So I will not explain it. So let me just quickly summarize. So in this work, we show the eigenversality for those random de Rieger graphs. As a conclusion, we get approximately 69% of those graphs are Ramanujan graphs. Although more than half of those graphs are Ramanujan graphs, but if you ask me to give you a deterministic one, you still need a number theory. We cannot. And the two key new idea in the proof, one is those microscopic version of loop equation. Hopefully it will serve as some general framework for the proof of those eigenversality, the convergence to the area one-point process. And the second idea is those generalized version of local resampling. It's just a way to take advantage of those randomness of the model, a way to show those equations. So any model you have some symmetry, you probably can explore the randomness, get some equations. And there are many other interesting random matrix models, like the one I mentioned, random uncovering of a base graph or polynomial of random matrices. It will be interesting to see if this approach will give you some eigenversality. And more recently, there are a lot of exciting progress in the world study random hyperbolic surfaces, and studied by many of people here. So one example is to study random surfaces sampled from Will-Peterson measure. And with the Hollis result give you some recursion for the volume under Will-Peterson measure. ENA actually identify those recursion by loop equations of some matrix model. This will also be interesting to see if loop equations can play more roles for those random surfaces. Thank you.
Questions?
So the concentration of a eigenvalue, say number n over 2, you said is roughly 1 over n.
Yes.
If there was some error term there, or it's a.
Oh, so the question is, so what is if I really look at the eigenvalue, subtract the classical location,
Right.
gamma I. So what is the
You
fluctuation?
That's little o1, right?
Yes. So this is a good question. Even for those Gaussian matrices or Wigner matrices, for that setting, you can explicitly compute it. So at the edge will be just a Tracy-Widom rescaled by n to the 2/3. And the picture in the bulk is slightly different. So if you really look at this type of eigenvalue, subtract the classical location, turns out it's a Gaussian fluctuation. And the size of the Gaussian is the square root of log n over n. So that's the little o1 term here. It should not be n2 power. It should be square root of log n.
I see. So for example, if I ask typically how many eigenvalues are bigger than 1/2, then it will be n over 2 and the fluctuation will be square root log n? Or?
Yeah, it will be square root of log n if you use exactly the number of eigenvalues inside the interval. But if you take a smooth test function, that will be of order 1.
I see.
Yeah.
Can you comment on the relation between this result and the universality result? Is this result used as input to your analysis, or is it completely independent?
Also, essentially, the eigenvalue rigidity result is a concentration of eigenvalues. Let me just use this Gaussian matrix case as an example. If you can show Mn is close to M sim circle, just get some bound for the self-consistent equation. This will give you the eigenvalue concentration. And now if you further identify the next term, it will give you universality. Like I think the universality is some further refined estimates of the first one. So
So you're not really using.
I think we don't use it, but as a byproduct to get those loop equations. Loop equations, once you have loop equation, that will automatically give you the concentration of the eigenvalues. So that is known, but now what's not clear is does they directly imply it will be a Tracy-Widom distribution or every point process. But for sure, we know it will give you the concentration of the eigenvalues.
By the way, do you know how to compute the Tracy-Widom without using Gaussian's method? Was it?
So you mean compute, you mean
No,
the densities?
what it is, because that's how you got your percentages.
Yeah, I only know it's the percentage. I get it by plugging mathematical. So if you really want, yeah, I only know that a Fredholm determinant.
Fredholm determinant.
Seems the only way.
So it does satisfy Pain-Lavey.
Yeah. So all those universality results, we never really compute those distributions. It's always try to show it's the same as the Gaussian matrix. And hopefully this calculation can give you another way. You don't need to compare with the Gaussian matrix.
Maybe I think so. Is there any hope? Suppose I would want some combinatorial properties of a graph that would give Tracy-Widom. So, and I don't want a random model. So, high girth, expansion, the right count of small subgraphs, whatever you want. Can you think of some combinatorial properties that would give the same bounds?
It's a very hard question. For example, like the girth, I feel like one consequence of this result is the girth probably doesn't matter because with high probability you will have triangles.
Sure, yeah.
So
I don't understand the question. I mean, the Tracy-Widom distribution is for a random variable. You're asking about deterministic graphs.
But there is something you want to know something about the graph that would basically imply
It's a second.
For what?
imply that it's
Let's say the bound for the second eigenvalue and for the last eigenvalue.
But what does it have to do with Tracy-Widom? Tracy-Widom is about random variables, right? So
maybe that's smaller than 2.
some condition.
the two, yes, that's a different.
Yeah.
That's just asking whether
Yeah,
you have a combinatorial property will give you
the
Ramanujan.
consequences of the
Yeah.
Tracy.
I think your result probably will more hopeful to get some identify something deterministic.
But I mean, you could probably say something like you start with the graph with certain properties. And then you do some switching of the edges, not enough to get a random thing, but enough to get Tracy-Widom distribution. That might be something which one could get, right?
By the way, the experiment that you're quoting of Miller and Co. was done by switching. That's how they generate their language.
I think they tested several models.
But that's the one that we like the most. Is it known that switching is mixing, exponentially mixing? Is that known?
Yeah, I think some n square or n to some power. So a lot of example I show you is for 3 regular graph. That one we can directly sample. It's just sample a regular graph. If it does not have a circle or multiple edges, then we output the graph. But if D is large, this does not work.
You mean because with high probability?
Yeah, with D to the minus some D squared, it will fail. So for D equals 5, it will almost for sure fail.
I'm a believer there's only 3 regular. Every other D is uninteresting.
Some number theorists believe that there are also other primes.
It's the smallest one.
Okay, so I think we'll thank the speaker again for